Hey guys, how you doing? Welcome to another calculus video. This is officially section 4.9. I don't know why our book does it that way. Really, we're starting chapter 5. This is a new shift. This does not really go with the stuff that we were doing with regards to extreme value theorem and optimization and all that stuff. This is kind of reversing the derivative process. That's the idea. We're doing something called antiderivatives. And so obviously if it's an antiderivative, it's the opposite of a derivative. We're going to reverse engineer the derivative process. So here's the idea. Since f of x equals x cubed has a derivative of 3x squared, then you know if f prime was equal to 3x squared, then you could say, well, then the function that it came from must be what? Must be x cubed. Well, yes and no. It's not quite that cut and dry, but it's relatively straightforward. Okay, there are definitely rules that we use, and most of those rules come directly from our derivative rules. They're just backwards. So let's take a look here at a couple of things. First of all, the definition. F of x, big F of x, we use a capital F to represent antiderivatives. Capital F of x is an antiderivative, notice the article, for f of x if big F prime of x equals f of x. That's exactly what we would expect it to mean. And so here's a fact. If f of x and g of x are antiderivatives, this said and, that means there's more than one. There could be more than one anyway, right? But if f and g are antiderivatives of little f, then g is equal to f of x plus c, where c is some kind of constant. C is just a real number. All right, now what exactly does that mean? Well, let's go back to this first problem here. If f prime of x is 3x squared, then f of x is x cubed. Well, yeah, that's true, but what if we took the derivative of x cubed plus 11? What do you get? You also get 3x squared because the derivative of a constant is 0, right? So when we go backwards, there could be constants over here that we didn't know were there, right? There could be, we have to have more information to get what this constant might be. So until we have that information, or if we never get that information, then we have to delineate the fact that our antiderivatives have a plus c that go with them, okay? So they have a plus c that go with them. Okay, so we need to figure out what our rules are going to look like. Here's an example of what we do with our rules. All right, so remember, the derivative for x to the power rule, very, very basic rule, one of the first ones we learned. You bring down the n in front and you subtract 1 from the power. Well, how do you do that in reverse? Instead of, you do it in the opposite order and you do the opposite of the rule. So we subtract 1 from the power. Here we're going to add 1 to the power. We multiplied by the power. Now we're going to divide by the power. And then as we discussed just a little bit ago, there needs to be a constant in there. Okay, so as an example of this rule, if we do the integral of x to the 7th power, what do we get? We get x to the 7 plus 1 divided by 7 plus 1 plus a constant. And so what do we get? We get 1/8 x to the 8 plus c. And here's one of the coolest things about all these antiderivative rules. You can always check yourself. You don't have to, but you can always check yourself. How do I check myself? I take the derivative. What's the derivative of 1/8 x to the 8th plus c? Well, bring down the 8. 8 times 1/8 is x to the 7th plus 0. If you get what you started with, it checks out. Okay? So here's a list of rules. I'm not going to go through all of them. This page will be available on D2L. In fact, you may want to go ahead and print it out from D2L and fill it out. Pause the video or something and fill it out. You can see, I'll zoom out a little bit here. All right, you can see all of our rules, and you have rules for constants. Constant comes out. If you're adding or subtracting, you can break up the integral. The antiderivative of 1 is just u. The antiderivative of a constant then would just be a constant times u. Here's the rule, power rule. Now, notice this power rule. This power rule doesn't always work. Where would we have a problem here? Where we would have a problem is if n was -1, because if n was -1, you get a 0 in the bottom, you're not allowed to have that. So this rule does not apply when n is -1. Well, if n is -1, that'd be u to the -1, which is the same as what? 1 over u. And 1 over u is the same as du over u, and that is the derivative of the natural log. Now notice we did put absolute values around that. That's important. You need the absolute values around the u. There's reason for that. Basically 1 over u can't be 0, but it could be negative, and the natural log does not work on negative numbers, so we have to throw in the absolute value. Integral of e to the u is e to the u. All the trig functions, pretty straightforward. And then we have these two inverse trig functions that match up. They don't match up perfectly with our derivative rules, but this a, we just throw it in there, and we'll do a couple of examples and show you how to play around with that. Okay, but for sure the u is always the variable. U is always the variable. A is a constant down here. A is the constant value. U is the variable. And I'm using u instead of x for reasons that will be clear in a couple of days. All right. One of our other methods, right? The u just kind of represents sort of like when we did a chain rule, you know, f of u type of idea where u is another function. We need to have that flexibility. So that's why we use the u in these rules. Okay. So what I'm going to do for the rest of the video is just show you a couple of examples. I'll do a couple, I'll let you guys do a couple, and then we'll end with one specific type of problem that will help you find out what the C is. In certain scenarios we can find the C, and we'll talk about how to do that. Okay. So problem number 1. We want to take the antiderivative. This symbol means take my antiderivative, please. Okay, so if big F is the antiderivative, then the integral antiderivative, those words are interchangeable, but that symbol is actually called the integral symbol. The integral of f of x dx is capital F of x plus c. Notice that this and this both go away when I integrate. These two go together. They're similar to, you know, when we wrote d dx, say take my derivative please. They're similar to when we had the limit out front. When we evaluated the limit, it went away. When you do the antiderivative rule, it goes away. The symbol goes away that told you to do that. Okay. Now, just like when we were doing derivatives, there are times where algebraic simplification of the integrand, that's what this function's called, all right, is appropriate. And so in this case, we're going to want to do that. We don't have an antiderivative rule for square root of x, so we're going to change that to x to the 1/2 power. We don't have a rule for fractions yet, so we're going to write that as x to the -3 power. And then all of those guys, we're integrating dx, and so now we're going to use our rule. The power rule is add 1 to the power, divide by the power. And you can do 5 in your head, that's fine. You don't have to write the steps. I'm just doing it because we're introducing the idea here. Okay, now when I add 1 to negative number, I still add 1, okay, and then the antiderivative of a constant, well, how do you get, whose derivative is 2? 2x, right? It's 2x, and then plus a c. Here's the one thing I do want. I do want you to simplify arithmetic. You do not have to simplify complex fractions and things like that, but you do have to simplify arithmetic. So 1/2 plus 1 is 3/2. I don't want you to leave this as over 3/2. I want you to simplify that a little bit further. Okay, this is 11x to the -2 over -2. And again, I'm writing every step. If you guys wanted to skip a couple of steps, that would be fine. You can leave this as x to the 5th over 5, or you can write it as 1/5 x. I don't care. They're the same. But here, if I'm dividing by 3/2, that's the same as what? Multiplying by 2/3. And if I multiply by 2/3, the 3's divide away. And so I get 2x to the 3/2. Here I get minus 11/2 x to the negative 2. I could put x squared in the bottom. That would be fine, but you don't have to. Plus 2x plus c. And that's your final answer. Okay, once again, guys, you should not have a calculator that can do this on its own. You should not have a calculator that can do integrals symbolically. They should be able to do the integral from 0 to 2. You're going to need that numerical integration, but not this. This would be a CAS calculator that could do something like this. You're not allowed to have those. So I'll need to see some work. If all I see is the answer, I'm not going to buy it. Okay, but certainly you don't have to see the 4 plus 1 and all that kind of stuff either. Okay, so that's the basic antiderivative rule, at least the power rule anyway, but there's lots of rules. Okay, here we go with secant squared x minus e to the x over 5. Remember that e to the x over 5 is the same as 1/5 e to the x, and constants just come along. So don't let that throw you off. It's not a quotient. Okay? And so if we go back to our rules, secant squared, the rule for that is tangent, and the rule for e is e. And so we end up with tangent of x minus 1/5 e to the x plus c. Got to have the plus c, but other than that, that's it. And notice again, this symbol and that symbol are gone. If those symbols hang around too long or disappear too soon, you will not get credit. Okay, you will not get credit because that notation will mess you up. It's kind of that whole thing about the chain rule. When do I know how to stop? Well, you have to know how to stop, when to stop. And so the same thing's true with antiderivatives. You have to know when to stop. You have to know when the rule's been completed and when you've done what the symbol's telling you to do. And when you've done what the symbol's told you to do, then the symbol goes away. Okay. Now, one more practice example here. 6t to the negative 1. I'm going to do this the wrong way first, and that is to add 1 to the power and divide by the power. I'm going to act like I don't remember that this is illegal, but it is. That doesn't make any sense. Can't divide by 0. T to the 0 is a 1. That's fine, but you can't divide by 0. That's no good. Well, that's because the power rule does not work for negative 1. It's not supposed to. What's another way to write t to the negative first power? 1 over t. So I get 6 divided by t dt. What's the antiderivative rule for 1 over t? Natural log absolute value t plus c. Okay. And that's it. This section, guys, is very straightforward. There's not a lot we have to do as long as it looks like one of your rules. Okay? If it doesn't look like one of your rules, you got to be able to handle it. So as an example, I want you guys to do this. You try this one. The integral of 2x to the third times x plus 9 dx. All right? Go back to your rules. There are no rules for a product. There's no product rule. Okay? There's no product rule. In fact, there will be times that there can be things you cannot integrate ever, right? Derivatives you can always do. You can always do a derivative. You might have to do a chain rule, then a product rule, then a quotient rule, then a chain rule. You may have to do a bunch of rules in a row, but you can always do them. There are functions that you cannot integrate. I'm not going to give you those. Okay? I'm going to give you ones that are doable, but you have to follow the rules that are given. There is no product rule here. You're not allowed to integrate each piece. So what else can you do? Pause the video, see if you can figure it out, and we'll come back and answer that. Okay? So thoughts? What'd you do? Yeah, distribute. Just distribute. Make this the integral of 2x to the fourth plus 18x cubed, and now I just have constants and powers. And so I can do that. I get 2x to the 5th over 5 plus 18x to the 4th over 4 plus c. I'm going to simplify that a little bit, as 4 and 18 can reduce to 9 halves plus c, and there is my antiderivative. Okay, just like that. I want to show you how to handle this rule right here, these two rules, or these rules here, this a squared minus u squared. It's not exactly the same. Playing the role of a and playing the role of u. All right, so we're going to take this arctangent rule because that's exactly what we have here. Remember that the rule is 1 over a squared plus u squared. Well, don't let the order fool you, because when you're adding, order doesn't matter, right? So u is always the variable, whatever's being squared as the variable. A is always the constant. 4 is 2 squared. So playing the role in here, playing the role of u is x, and playing the role of a is 2, and now you just plug it into the formula. 1 over a arctangent u over a plus c. Okay, so this just takes some practice. It's following a formula. That's all it is. And we'll actually do a more general version of what's known as u substitution, or defining a u, like we did with the chain rule when we were differentiating. We'll do a more formal version of that in section 5.5, which is actually the next section. We're going to jump from 4.9 to 5.5, and then we'll come back and do the other things. But I want to be able to show you guys kind of some of that stuff all together. And so that's the idea of how to use the arctangent. And arcsine would be similar. The one thing about arcsine is you always have to have the constant first, because it's a subtraction. Underneath the square root is a subtraction. And so you need to know that. All right? So now, I told you that we would have an example where we have to find the c itself. And notice that there's extra information here. We're given the derivative, great, but we're also told one point. This is called an initial value. Okay, and so that means that we're given one specific piece of information about the original function, more than the derivative. The derivative is given, but we also have to know this one extra piece. So, step one, we got to find f of x. Well, how do you find f of x? You have the antiderivative of f prime. That's how you do it. So we want to take the antiderivative of 3x minus 9 over x cubed, which is great, with one exception. There's no quotient rule. There's no product rule, there's no quotient rule. Well, what are we going to do if there's no quotient rule? Give it a shot. See if you can figure it out. We already did one where we didn't have a rule. We had to mess around with it a little bit, right? Pause the video and see if you can figure out what you have to do next. Okay, so what did we have to do? Break up the fraction. Let's make this 3x over x cubed minus 9 over x cubed. You could have also brought it up as x to the negative 3 and distributed. That would have worked too, because this is going to give me 3 over x squared minus 9 over x cubed, and I'm going to have to eventually make those negative powers anyway. So if you would have made this x to the negative 3 and distributed, you would have saved a step. That would have been great. Okay, so now we've done all the algebra. Time to do the rule. Time to do the rule here. What's the rule? Add 1 to the power. Negative 2 plus 1 is negative 1. Divide by that new power. Add 1 to the power. Negative 3 plus 1 is negative 2. Divide by that new power. Get a plus c. And now that we've done the rule, now we can manipulate our fractions if we need to. Rewrite our functions if we need to. So this is f of x with a plus c in it. But step 2 now, we're told that f of 1 is equal to 3. We're told this initial value. What does that mean? That means if you plug in x equal 1, you're supposed to get 3. So f of 1 would be negative 3 over 1 plus 9 over 2 times 1 squared plus c, but that's supposed to be equal to what? 3. So now I can solve that for c. I get negative 3 plus 9 halves plus c equals 3. Negative 3 and 9 halves is 3 halves plus c equals 3. Subtract 3 halves from both sides, you get c equals 3 halves. That's not the answer. The answer is f of x equals negative 3x plus 9 over 2x squared plus 3 halves. The answer is your single function that fits both of these categories. It has this derivative, there's a lot of those, and it has this value. There's only one function that has this derivative and has this one special value. And it's this one right here. Cool? All right, so that's the only other kind of question I can really give you. You guys have got to bust it over the next couple of days and learn these rules. Okay, again, it's, you know, for our class, you can have these rules out. You don't have to memorize them, but they better be really comfortable. And if you have a function that doesn't look exactly like one of these rules with a different letter maybe, but that's it, you can't do it. And you're going to have to manipulate or do some algebra in order to rewrite it so that you can do it. Okay, that's the key. Don't force it. All right? As always, let me know if you have any questions, and we'll see you later. Thanks.